My name's Charlie Mydlarz, and I am a research associate professor at NYU, and I'm part of the FloodNet team. And we are kind of consortium of researchers and city agencies who have developed a sensor network to monitor real-time urban flooding. And it's a great group. It's NYU, groups within CUNY, the ASRC, OTI as part of the city, MOCJ, SJIRB, DOT, and DEP, who actually fund this project. So they have provided the funding for us to deploy our sensor network. So thank you to all of those people. So what is the sensor network? So we've deployed around 250 flood sensors across New York City so far. We started back in October 2020 with our first sensor, like sensor number 1, and now we're up to 250. And the aim is to hit 500 by the end of 2026. And we are currently the largest street level flood sensor network in the US. Nice caveats, right? Street level flood sensor network in the US. So we've captured about 1,400 floods so far, and this is where we are deployed. And you can go to dataviz.floodnet.nyc to see where our sensors are located. And we've kind of covered the 5 boroughs, but we are expanding, and we should be growing soon. So just a brief intro on how the sensor works. So we are able to sense water depths with an accuracy of around plus minus an inch. We collect measurements every minute, transmit it wirelessly back to our servers, and store the data and visualize it for analysis. We are solar powered, battery powered, so we don't need any power infrastructure at the deployment locations. Deployment locations are typically what they call drive rails or street signposts, the ones you check when you park. And we have designed these things to just operate autonomously. So you deploy and you technically should be able to forget, and they just collect data every minute, sending it back to our servers. And to be scalable, we want it to be low cost. So the parts totals about $250. That's a misleading number because the cost per sensor per year is a much more when you factor in deployment, maintenance, and kind of all the infrastructure that supports it. But still, you keep the cost of the sensors down, you can be more scalable. And I have some videos that I'm going to try and start. Whoa. Okay. So this is Tropical Storm Ophelia, and it's not referred to as that for people who know. It's the remnants of Tropical Storm Ophelia. So this is, our sensor is right there, just in the corner. And this is like that people may have seen this as it happens, but it was just an incredible sight in kind of the deepest part of Brooklyn, Carroll and 4th Street. Lots of restaurants, bars, businesses with basements where they store produce. People live in basements, and there were some deaths during Ida mainly, but huge impact. And we have another coastal event which we captured. So this is us doing some ground truthing, which involved just having some pizza and some beers and watching a coastal flood roll in. This is down in Hamilton Beach. The sensor is right there. I'm sat there just kind of measuring with a ruler for an hour or two. But it's great. So this is a coastal flood in action. You see the trash cans start floating around. Like this is a very frequent event that you see on the coast, and we'll show you data to back that up. And there it is. And just an intro to the data. So it's kind of hard to see those blue lines, but what you're seeing here is Beach 84th. We're going to refer to this sensor a lot when we talk about the data. It's one of our favorite sensors. It's down in the Rockaways. And what you're seeing there on those darker peaks, what looks like a tide gauge data set is actually a flood data set from FloodNet, and that's showing street inundation happening with the high tides coming in and out during a full moon event. It was a particularly high tide. Actually, it wasn't one of our highest. It's like a 16-inch depth at peak, and it's probably hard to see on the slides. Can you see like a lighter blue kind of tide? Yeah, it's hard to see, but that's the nearby tide gauge. It's probably, can't think of inward. Yes, it's a nearby tide gauge. So we're perfectly synced up to the tide gauges. So that location is overland. All our sensors are overland, but it's flooding like it was a water body. So Ida was really the event that put us on the map, and I don't need to explain Ida, but we detected incredible speed onset of floods. There was like a 15-minute onset from 0 to like 35, 36 inches. So very fast, very dangerous. Again, in that very urban area that you can see. So at that point, we only had a few sensors. But what we were able to do was send out alerts. We were sending alerts at that point to city agencies. So we had a number of agencies signed up, NYC, DEP, NYPD, and FDNY. So we were sending out email alerts at that yellow line on that bottom plot. And the city technically wasn't aware of the extent of the flood until that red line where calls started coming in from cars that was stuck inside the water. The fire department was coming in with their high axle vehicles to try and extract people and like rescue people from that situation. So that really piqued the interest of the administration and the agencies, and then we were funded soon after Hurricane Ida. So we have a bunch of data products. We have a public-facing dashboard at dataviz.floodnet.nyc. We collaborate with the people at NYC Floodwatch, which is a MyCoast program under Sea Grant. And they produce printed neighborhood reports that uses our data. So like accessible PDFs that residents from different neighborhoods can see and see the history and flooding over the previous quarter. We export all our CSV data daily so people can grab CSVs. We have an API as well. And that has a number of active users from many groups. We send out alerts via email when any sensor triggers, and an email goes out and links people to a dashboard that you can view data in real time. And we're working with NYC to develop ArcGIS layers so that the data can be integrated better into city agency tools and platforms so they can better use it in their response to flooding. And what we're going to talk about today is our impending, soon-to-be-released flood event data set, which we're going to be putting up on open data. And we're very excited to talk more about that.
Yeah. So the flood events dataset consists of the sensor metadata, and this just has all of the relevant associated information with the sensors, like the geographic information, the date it was deployed. If the sensor has been retired, it'll include the date it was retired as well. Potentially mounting information as well, to give you a bit more insight into the mounting conditions. And you can use. So then you take the sensor ID from that table and you can join it with the flood events table. And the idea there is to just link a sensor ID with a start time and an end time of the flood event. And to extract the events, what we do is we look for any changes in the depth relative to our belief of where the ground is. And we mark that as like the start of an event, and then the end of the event is denoted by when the belief returns back to the ground. And so each row in the dataset consists of a single event from a single sensor. If you want to look at, say, a storm event like Hurricane Ida, you would just select the time range of storm event and select all the sensor events within that. And we also just have some basic metadata, such as like the peak depth, the accumulation time, the drainage time, a few others, just statistics, as well as a data column where we just include a full JSON array of all of the timestamps and depth measurements within that time range. So all of the plots that you see can be made fully from the data that will be released on open data.
So where are the sensors? I mean, you've seen the map and you can look at the map now. It's hard to see the map beneath there, but across the 5 boroughs, and majority of our sensors are in Queens, large borough, and predominantly has coastal flooding as an issue. So Queens is our kind of primary borough at this point, and we have around 1,400 plus flood events across 50 neighborhoods. So we're going to start looking. Oh yeah, sorry. The distinction between coastal sensors and pluvial sensors. Pluvial and coastal. So pluvial sensors are defined as sensors that are mainly flood due to pluvial conditions due to rainfall. Coastal sensors, mainly driven by tidal influence. However, a coastal sensor is also subjected to rain. So They could be compound flood events or pluvial flood events on coastal sensors. So, so that's something to keep in mind. But we have far fewer coastal sensors, but you'll see the data shows that we have way more coastal floods. So breaking it down by neighborhood, here's Brooklyn. Good few sensors in there. I'm not going to spend too much time on these, but looking at the top 5 sensors that we have in Brooklyn by annual flood rates, this is normalizing by flood rate per year. And we have sensor 1, Hoyt & Fifth at number 1, which is great. So this is controlled for duration of deployment. So it's not just because it's been deployed for longer that it's showing more floods. It just floods more at a higher rate than other locations. And this is in Gowanus. It's at the bottom of 2 hills. So it just naturally, water pools, inundates much more easily. And it has a drain that is just blocks very quickly. It's by a Superfund site with a lot of construction vehicles coming in and out. So that the drains block much more readily than other locations. We've got, you really can't see that map, but that's Williamsburg, South Williamsburg there. It's a very kind of low-lying area, lots of pluvial runoff into these locations. So those counts are primarily driven by, all pluvial events have hit South Williamsburg in quite an extensive way. Most of our coastal sensors are actually deployed in Queens, as you can see. Yeah, it's hard to see, but the coast is, I can't even see that. The coast is around here somewhere, right? That's like a Jamaica Bay, I think. Yeah, it's down here somewhere. So most of our coastal sensors are deployed in Queens. Maybe, can we turn the lights down a little bit? Maybe that will help. Just so because all our maps are really light, so we're not going to see many of these maps. Yeah, most coastal sensors in Queens. Beach 84, one of our most favorite sensors, which is right here, which is on the coast. Beach 84 is suffers a lot. Like that street suffers a lot and has captured 90. Its flood rate is like 90 floods per year on average over its duration, but like 90 on average per year. It's pretty extensive. It's a common occurrence. Coastal flooding happens monthly. It's happening all the time. It's very impactful. And Staten Island, Ricardo, our colleague, is going to talk more about Staten Island later in the talk. But yeah, we have a fair few sensors in Staten Island. A kind of mix between inland and kind of coastal sensors there. And some of the top candidates, Grimsby and Mapleton, which Ricardo is definitely going to talk about, is one of our topmost flooding locations, which is in the Midland Beach area and fairly close to the coast. But Ricardo will explain why that one floods to the extent it does. And then Manhattan, primarily pluvially driven, but our least amount of floods captured. But it's also, we've had our sensors deployed for the least amount of time in Manhattan. So it's not saying it floods less there, but we haven't detected as many floods there. But it's primarily pluvially driven, although that might change with the next event. So they're relatively new, so we haven't captured many flood events. That's why you see those numbers on the plot. They're kind of in the small single digits for rates. The stars on each of these here, it's very hard to see, shows that we haven't got a complete year of data for these sensors. The Bronx is really interesting. We've had a lot of fun looking at this data over the past few weeks. So City Island is a fascinating place. It's a great place to visit if you haven't, but it's a fascinating in terms of flooding. So we have one sensor that just drastically dominates. And this is Ditmars and Hunter Avenue. It's an interesting location. It's kind of at the end of a roadway. Outside of the end of the roadway is the water, is the bay. There's a blockage, there's like a barrier at the end of the roadway, which seems to catch and hold water. And it's also down a hill, so it has a pluvial runoff issue as well. And it captures, is the highest rate, isn't it? Across all of the floods, or all of the sensors. Yeah. It's,
oh, really?
Yeah, it's incredible. It's always firing alerts, and it has very strange profiles of floods, which we'll show you. So you can't see the other blue, but that's fine. You don't need to see that. What you're seeing is the sensors deployed over time. So going back to the start, October 2020, before funding kicked in. Where did that come in? Here. You can see what funding does to a project. accelerated us greatly. We tapered off recently. We were going through a phase of maintenance and kind of revamping certain aspects of the hardware and the back end. So deployments have slowed of recent times, but then we're ramping back up to meet 500. There's not a continuous increase. You kind of have to stop now and then and focus on different things like maintenance. And B.
Yeah, so just to give you a better sense of how coastal flooding differs from like inland pluvial flooding, these are plots of 7 months of data over the same time ranges with coastal flooding at the top. And you can just see the frequency and the regularity of the coastal flooding. And you can see it sort of follows like the monthly lunar cycle. Whereas the inland flooding is much more irregular, but when it does flood, it can be have like catastrophic heights. Like the bottom maximum is like 36 inches or 38 inches, whereas the coastal flooding's axis is like 2 feet. Yeah. Yeah.
Xerophilia?
Yes, it is. Yeah. So this is zoomed into a single month's worth of tidal flooding, and you can see the the progression of towards the full moon, and then receding as we move towards like a new moon. And another thing to note is just how like synchronized the sensors are. So like when it's flooding in like many places at once. So, and this is just, oh, Jesus Christ.
This is the best looking plot in the whole presentation, but it's hard to see.
Yeah, so this is a look at just a year's worth of flooding at a single sensor overlaid, and you can just see like the regularity of the shape of the.
Keep talking. I'm going to try and change something.
All right. Yeah. So you can see how regular the shape of the flood contours are, meaning it's just a very like consistent flood pattern. And you can also notice that like as the max depth of the flood grows, the drainage time like extends out further and further. So there's sort of that like disproportional drainage.
You can see the main cluster here, right? Of like, this is event duration versus maximum flood depth. So you can see the main cluster there. There are outliers running out here. You can kind of see it if you really squint and imagine. There's data here, there's data out here, there's one point up here. So most events are less than 1 foot and shorter than 4 hours. But there are some events that are up to 40 inches and last for 11 hours. Like that's deep and long. That's a really, it's very impactful to have water on the ground for that long, especially when there's infrastructure underneath, there's homes, there's all the things of the city there. And, there are points up here. So, long floods, very deep. And that brings us to, I can see that. So this brings us to the major flood category. This is floods greater than 24 inches that we've captured. The last one that we saw, the outlier I pointed out, was from Davenport Court in Howard Beach. You can see that. Where's Howard Beach there? That's this one, right? So there is some you see the long tails here. Some of these sensors, it starts to reveal more than just basic flood depths and other things. You start to see things like drainage rates, which becomes quite interesting. It's like, what is happening in the infrastructure at that location that means that water is held onto in that way? And that's likely, that's going to be a coastal event. So that's a tidal event, and the tide is doing its usual cycle, but the water hangs around. What is it in that system? How is the drainage impeding that water from draining out from that location? So we can start to think about the use cases that the city may have for this to try and understand more about what's going on there, open up sewers, kind of expand the drainage situation in those locations. So to better kind of cater for those situations. that crazy one off to the right is our favorite kind of outlier, Mydlarz. You see the way it comes up and then it peaks? So it's a different system to the other locations. There's some complex topography going on there, and it's a fascinating sensor. So it's worth going to that location. You can go on a sightseeing tour of floods in New York. And this is IDA. This is the one that we before we were funded, capturing some really intense flooding events. The duration of these are important. They're quite short-lived, but very deep, very fast. This was our network at that point. I think it was only 3 sensors, or at least 3 sensors that captured IDA. And it was really, it was the one that piqued interest. Also at this point, just some detail about the data, we sampled at 5-minute intervals. We did switch out our techniques throughout. So we were 5-minute sampling, now we're 1 minute. Mainly driven, that change was driven by this event. We didn't expect water to accumulate that fast. So we thought 5 minutes is a great sample rate, but it wasn't enough after seeing IDA and seeing how fast the onset was for that. And we should also note as well that we are smoothing the data in these plots, and we do plan to release the data smoothed. So we've kind of weighing up the trade-offs for that, but we feel, and we're open to feedback. We'd love to hear people's thoughts, but smoothing kind of removes some of the low-level noise that the sensors typically have. They're systematic noise, so it may help with interpretation and other things.
Yeah. And this is September 29th, which Ricardo will talk more about. But by this time, the sensor network was much more extensive. Like, we had sensors in a lot more places. And yeah, I guess we can go to the breakdown. And yeah, so this is the profile is broken down by borough, just because there are so many, it's hard to see when they're all overlaid. And we can see that, like, most of the flooding you can see is in Brooklyn and Queens, with Williamsburg and Howard Beach having the most number of flood events captured during that event. And I guess maybe pass to Ricardo for.
All right. Hi, everybody. I'm Ricardo, Toledo-Crow. I'm with the Advanced Science Research Center, part of CUNY. And I'm going to be talking about work done by my colleagues at the College of Staten Island, in particular about what Michael Kress has been modeling for us. And what we are doing is that we are going to be analyzing a very specific location during that event on September 29th, 2023, the remnants of Hurricane Ida. So, what you have here on the left is Staten Island, and then a little dot with color. That's the Midland Beach neighborhood. And in that neighborhood, there's a little intersection of Grimsby and Mapleton that's gone through a lot of problems with flooding. The photo in the middle was taken a few years ago, when this neighborhood was seriously flooding. There was a lot of disruption, a lot of houses being sold. But around that time, there was this development coming online called the New Creek Bluebelt Project. And that was modifying the natural water wetland that's next to this neighborhood. And this is a view of the neighborhood. And you can see back here, this wetland has been modified to produce a system to catch the storm waters, right? So what we have is we're modeling this, how this system has been improving or not the flood situation in this neighborhood. So what Mike did here is that he took all the hydrology and the hydraulics available at the time. I'll talk about the sources. And he modeled 3 catchments shown here in light blue, light yellow, and light purple. Can you see it? Yeah? Okay. And so he put all of this through a modeling system. And we have one sensor in particular right there at the corner of Grimsby and Mapleton, and so he did the modeling, and we'll be comparing it with the ground truth provided by our FloodNet sensor. Okay, so this is what happened during that event. Here on the left, you can see all the flood sensors that we have in the neighborhood, and then on the right, you can see the time of the events, of the flooding events. And of course, the first sensor to report flooding is the one that's closest to the lowest point of this New Creek Blue Belt. That starts to fill up, and it pretty much continues full all the way throughout the day and into the next day. But then on the other hand, you can see that as the water is flowing downhill, you start seeing all the other flood sensors start reporting increased flooding. And just to as an example of the usefulness of this, the DEP saw this long tail on that sensor and actually sent out a crew to see what was going on. Probably some of the storm sewers were getting clogged up. All right, so the model itself, I'm not going to go into the details, just to point out that it includes a lot of moving parts. It has all the hydrology and hydraulics. It has different sources of water. It has different sinks of water. And what we're doing is we're taking data from the open data available for New York City and incorporating to the best of our ability, or to best of Mike's ability. And of course, a lot of this information is not available, particularly things like the drainage pipes. They're not available. We're thinking about actually going for a FOIA for that. So a lot of assumptions had to be made, but nonetheless, I think that the results will speak for themselves. These are the sources that we use for data. So there's a lot of digital elevation models that are available on NYC Open Data, the surface permeability and the surface types. So you have like buildings, you have roadways, and the catch basin. So the city does provide the location of the sewers themselves, even though the exact piping is not available. We use something called the stormwater management model, which is a model that was put together by the EPA a long time ago. And for those of you who were here last year to this talk, I presented this, but we had only worked on the campus of Staten Island, of the College of Staten Island. Now we took it out to the streets of Staten Island. And finally, the final tools were ArcPython and Mydlarz. All right, and these are the results. And what we have on the top here is the input, which is the rainfall during this event. And this was captured by one of our rain sensors. Believe it or not, we have a few rain gauges, part of FloodNet, that is located on a building that's not too far away from this neighborhood. And then in the middle, you can see the simulation at that location of Grimsby and Mapleton. And then on the bottom, you see what the sensor actually picked up. And first of all, I want to point out that the depth of what we modeled was almost too good to be true. And the reason I say this is because our sensor is not actually looking directly on the lowest part. We're always looking at about 4 inches from the street level. So there's obviously an error of at least 3 or 4 inches. And then what we also miss is that tail end of the actual flood. But I think overall, this is a pretty good agreement with the model. So what does this mean? This means that modeling this neighborhood can probably allow us to get a lot of information where we do not have sensors, right? So if we model the entire flooding in the neighborhood, we ground truth it where we do have sensors, and then we can have a certain degree of confidence that any other position in the neighborhood is modeled. All right, so the other part of important thing to mention is that this Blue Belt system that was built, it was finished a couple of years ago, I think, apparently has done a lot to improve the duration of the floods. So it has not eliminated the floods in the neighborhood, but it certainly helps to clear them out a lot faster. And that's all I have. Okay, well, thank you very much. So,
We've got loads of time for questions because we kind of blasted through that, but that's good.
A question on the last chart there, on the stormwater management model.
Oh, yeah.
You see the first spike of rainfall there, hitting about 6 hours before the flood does. Is the reason that doesn't correlate with flooding is because the stormwater management model will incorporate things like how wet is the ground, how much accumulation has been once it reaches above that, then or time to drain.
there's a capacity that has to be, saturated and
And also at the sensor location is nearby the bluebell. So when bluebell catch all the waters from surroundings, so that there's a source system, and there, when the water reach higher toward the street level, so it's street level, the water back not beyond. It take a little time to fill the reservoir.
of course when the bathtub over, it's a catastrophic.
Question. Are the sensors kind of organized or categorized around the, I guess, kind of like the stormwater systems that they track to the degree to which you could isolate like this particular part of the storm sewer is draining slowly because of these sensors, as opposed to
Well, the kind of the locations are drawn from a bunch of sources, like where we actually deploy, and ranging from.
or I guess another way to put it is like, can you tell that all of these sensors are tracking water that would go out of this this part of the storm system?
Technically, you could, if you knew or if you had all the data on the drainage systems beneath the ground at those locations. We've not done that analysis, at least not at scale across the network, and some of that data is hard to get. I think the sewer data is impossible to get. Yeah, it's sensitive. So you technically could, if you could access that data. And we were in locations, we base a lot of the locations on resident suggestions. There's a big community engagement effort on FloodNet to raise awareness of flooding, to engage residents with the technology, and I get their feedback on where we should deploy. And also we use the stormwater maps that DEP has put together. And those stormwater maps do factor in, they don't factor in all the sewers though, right? It's a subset of the sewer systems. So if you've seen the stormwater maps, there are just blue areas. There's a map online, there's blue areas where flooding is modeled to happen or projected to happen at different levels. So we tried to be within those areas as well. Yeah, if that helps.
Yeah, and to that point, the model that Mike put together actually does include some of the sewer information, but that is the information that was provided when the Blue Belt was proposed. So it's not really as built, it's more like as you would like to build it. So everything else had to be I guess an interpretation.
Thanks for this presentation. This is really interesting, and I knew nothing really about measuring flooding with ultrasonic sensors. But I'm wondering, if all the sensors are directed specifically at impermeable surfaces, for example, or if not, if it may be possible to get any elements from like the background noise of like soil moisture in some sites.
It's ultrasonic. The sensor is ultrasonic based, so really it's a rangefinder at its core. It's just bouncing ultrasound off a surface beneath, and you stick to a rule of mounting above hard surfaces. Permeable surfaces are typically difficult to measure from because they're either grass or earth, and they bury, and they interfere with the reflections. So we're typically over sidewalks. So it's a major limitation in that we can only deploy where there's infrastructure and where there is a hard surface. The most difficult thing about the data we collect is it's when there's no flooding, because then you've got the kind of variability of the street and whatever happens beneath, trash, bikes, grass, growth, everything. Yep. Yeah. So, but when there's flooding, a clean sheet of water is easy compared to the general surfaces we measure over. Yeah, I'm not sure that answered your question.
Yeah, that's somewhat. Yeah, but insightful. We're another first thinking.
Yeah, thank you for the presentation. I was wondering, like, how much does it cost to install a sensor? And can you explain a bit about, like, how many more sensors do we need to ensure accuracy? And what's the trade-off?
It's a big question. The first question, the cost, it's difficult to pinpoint, but it's, you say 250 per sensor, that's like a fraction of the cost of the sensor. In reality, it's at a very rough ballpark, a few thousand per year per sensor to have them existing in New York City, right? Including that factors in a lot of things, R&D, deployments, maintenance, backends, right? There's like a team behind the sensor network. So there's a lot of factors in there. The second question of like how many, it's really hard to say. It depends what you need it for, right? So do you need one on every block? Probably not, but like to accurately cover the city for this case, it's really impossible to say. You'd probably, it'd be nice to be in every location where the models say it should flood and where residents say it should flood. And that's thousands of locations. We have a sensor suggestion form that you can fill in on FloodNet.NYC. So we want people to tell us where to put sensors, and thousands of suggestions so far. Yeah.
We have mentioned it, but a very important part of FloodNet is sort of the community part. We have like a whole community manager and outreach. So it's a lot of reliance on the public, on the neighborhood residents to tell us where it floods, why they would want it here. So that was a big part. The effort is just to get the information where to deploy these things, and then how to choose which were the more important ones. Because they're competing interests. There's the neighborhoods, the residents, there's the city agencies, and then of course us as scientists, we would like to measure here that maybe it's not immediately applicable, but it might help us with models that we came at.
It's important to the community engagement element. So many reasons why we do it, but also to let people know what's going up in their neighborhoods. Because these things look fairly ominous if you don't know what they are. Microphone, camera, you don't know. So we've put signage up beneath all the sensors explaining what we're doing, and then that can help. It raises awareness, and you can also kind of inform people what it's doing. It may reduce vandalism of the devices and maybe some knock-on benefits as well.
Have you explored the relationship between the flooding and green infrastructure assets that are put by the city?
The city, yes. South Jamaica Houses is one project where we deployed a number of sensors. There's a big green infrastructure it's not GI actually. They're building a huge catch basin under a basketball court. And it's going to be able to accommodate a huge amount of runoff and stormwater. There hasn't been a flood there, but we have a number of sensors around there. So we're capturing that kind of before. And the project is due to finish or is finished. I can't remember if it's done yet, but the hope is that we would try and you can measure the efficacy of these interventions. And there's been like the blue belt, yeah. And there are smaller smaller GI projects that have gone up during the life of our sensors, like some rain gardens, those kind of smaller interventions. And we've not done an analysis on the efficacy of those yet, but the data's going to be there, so we can do that.
If we've had a quiet season,
it's been really quiet. It's not been many floods. It's just great for the city. Yeah, exactly. FloodNet was quiet for a while, which has given us time to deploy more for that next event, which will come. Yeah.
Have you, sir, you said 250. Do you know the locations of the remaining 250? I know you talked about the process of getting locations, but yeah. And then my other question was, what is the lifespan of a foot sensor? How often could it need to be replaced?
So the next 250 we kind of work about 3 months in advance. So we know where we're going for 3 months in advance. And I can't tell you off the top of my head where we go next. The Bronx, expanding in the Bronx is one of the locations. Astoria is going to get more sensors. Now I'm looking at a map. Rockaways, CUNY, Seagate, those kind of areas. Staten Island, there's more going up in Staten Island, more in northern Manhattan. Williamsburg, I think, is also due to get some more. Rosedale, Flushing, North Flushing as well. Yeah, like the next, we kind of know the next 3 or so months of where we're going to be. And the second question?
Oh, the lifespan, or how long a flood sensor can last.
It's kind of like we're still working it out, to be honest. I'd say that we visit a sensor roughly every 6 months currently, but we're always updating and refining the code and the hardware so that should get longer and longer. Because for this kind of phenomenon, you need years of deployment to gather many events. So, we've had sensors that we've rarely visited.
Beach 84 has been there for,
Beach 84 is fantastic.
it has been there for 4 years.
Yeah, great. It just sits there, just sensing. It's actually a different design. It's the same sensor core, but it's inside a pipe. So if there isn't like a signpost there that we can mount to, we have an 8-inch pipe, painted green. It blends in. It sits there with holes in the bottom. The sensor's inside the pipe, and it straps to fences or various things that we can't strap a external sensor to, or places where there isn't a hard surface. It gives us that option. We have 2 of those at Brookville Boulevard, Snake Road. Incredible place. Like we tried to deploy there twice. The second time, we had to rescue someone because the road was flooded out. The car had tipped over. It's crazy. Like this happens very frequently. It's only when you see it that you kind of realize the extent. But yeah, the longer they last, the better. That was the driver for like solar power, battery power, remote connectivity. All those things are really important.
Thanks for the presentation. I have a question about the lava like part of this. Also, like I seen that like this is kind of like a very physical model of the situation. I just wondering like if there's also attempt to like maybe try a very generic machine learning model and just see how that benchmark gets that type of your physical. Although I know probably glancing over a lot of details in terms of what goes into the machine learning and what's a variable you will use to do this kind of model, but have you there like charts type? I think I saw something similar with like urban heat index. Oh well, yeah, urban heat index earlier in the week. I do this kind of thing.
This is a very traditional physics-based model. This is like, size of pipes and permeability and stuff like that. However, the output of this might help what you guys are doing, no?
Mm-hmm. Yeah, I mean, the machine learning that we've worked on currently has just been like flood versus noise classification for that type of filtering. So we haven't really done any of the simulation. And I feel like that to do that with machine learning kind of requires a greater scale of data. But we're getting there. So like, I don't know, 2 years ago or a year ago when we were doing more of the machine learning, we didn't really have that much. So I don't know, possibly
In a few years.
a few years. Yeah.
Last summer, we used the sensor data on Staten Island. I think it's 30 sensors. So we did a planetary machine learning model independent to the physical model. I think we modeled that September that wind data. We compare several different learning algorithms. It's come pretty good result. Our thinking is because for the area we don't have a sensor coverage, right? If we can use machine learning, found a certain patterns, that will. Or we can predict maybe some location need to install sensors. That's the reason why. Second reason is we are starting looking into it. You can see the physical model. You need to put a lot of parameters to make it work. Okay, and sometimes the model it can only be good as the data you can collect. For those physical parameters, sometimes we don't have. That's very good data. So what we do is we try to use kind of a machine because we luckily have sensor data as a burning target. We want to use those sensor data to train the model how to just become a set of good parameters. And then we can use that parameter once we tune into this parameter. So they use the parameter to predict all future rain events. So it's a it's a balance between the physical model and the machine learning.
There's some very simplistic things that we're trying also, not machine learning based, but just looking at like a 0.0, right? For coastally driven sensors, when we see an inundation starting at the coastal sensors, what depth is the nearest tide gauge showing, right? Is there the respective tide gauge at? So you can then leverage the kind of very established tide prediction models to estimate and predict what level of inundation you would be expecting with a given tide gauge level. So that could really be useful for, I mean, this is already used by Hamilton Beach residents. We have some power users who live in these neighborhoods, and they are tuned in to our sensor data, and they're very tuned into the tide gauges because they know that when a tide gauge hits a point, move your car, and then, it's going to go that high, empty the basement, do all those steps that these residents have to take very frequently.
Yeah, something that I have noticed is that you can see the different floods during the tide events are actually slightly offset from each other, which means that not every single neighborhood will flood at the same time. And that 20 minutes difference could mean your car will be flooded over or not. So the residents really rely on this to move their cars out of the neighborhood to higher ground. Because, I mean, in practical terms, if you get salt water into your cars, it's a big hit.
Well, first and 104th, that fourth one down red, that's the only road out of the Hamilton Beach area. So when that floods, if you're not out by then, you're not out. You're kind of finding high ground on a very small patch of land. It's risky.
And then
how do you deliver the data to city agencies so they could incorporate it so they're just...
It all goes back to a city managed, or it's a city Azure cloud setup. So we have all of our databases live within this Azure environment, and it's plugged into a bunch of visualization tools. A key thing we're doing that's been great is working with NYCM. So NYCM are building an ArcGIS layer that takes our real-time feed. So rather than introducing to the city, look at this cool dashboard that you need to learn how to use and integrate, they can integrate an ArcGIS layer, which is, the city's an Esri shop, so they can just build that into their existing tools that they use. I mean, most agencies have an ArcGIS map interface, especially the emergency response agencies. So we're another layer on that, and we're still working with them on that, but saves a lot of the kind of learning curve to engage with the agency. So,
And they ingest that just by calling our API.
Yes, work.
This is just one of the most exciting projects in the city. I want to thank you guys, and this is just I wish we had this data a decade ago, right? This is you said this is the biggest sensor street level network in the whole country or something.
The sales pitch, yeah.
That is so cool. So I guess first, something that I'm very interested in are those drainage curves. So we have rates of floods. What we don't have good data for is recession. We have flood hazards, FEMA's layers, vendors have 100-year storm return periods. What we don't have as a field is that receding curve, right? That's what we want. So two places can flood the same max, but that recession curve is different. I'm just very interested of your thoughts about analyzing that second curve, that rate of recession, because we kind of expect places, cities, urban areas to flood, right? That's just, it's impervious surface. What are your thoughts about that rate of recession, and what's NYU doing about studying if Jamaica Bay floods, looking at the recession rates and things like that?
I'd say on the operational side, I think I briefly mentioned it, but that it is an indication of a drainage issue, right? Simply in the city, the DEP could potentially go out and remedy that issue, what happened at Grimsby and Mapleton. But coastal sensors, we've got examples here. You can tell there's some impedance.
Yeah.
There's a push that the water's struggling to get out, and you end up with 10, 12 hours of inundation after a peak event, which tried to drain, but just couldn't, versus, you say, other events that just drain away fairly well. So, from that side of things, it could be, it's actionable data, I think. We've seen, I mean, some places where it just sits around for 16 hours.
Oh my gosh.
Yeah, it's like it would not doesn't necessarily deep, but it just stays.
Just like ponds.
When it's salt water, just ponding and just be staying there.
Question, please. Like, I'm sorry. Second question. Like, that's it. I note that we don't have like pipe data. We have manholes, catch basins, outfalls. What are your like ideas about using street segments as like pipe? And like we have like standards in the city. Can we connect catch basins, manholes, outfalls, and just say like a pipe is underneath the street because that's how like pipes are like laid? Can't you build your own swim model with just like street segments as like a pipe?
I think that really goes to what Zanya was mentioning. So yes, indeed, we have the elevations, we have the gradients, we have the catchments, and then you can take a smart, uneducated guess as to where things go. But the city does lay things down with, I mean, it does build in gradients into its plexus. And especially at that point in Mapleton and Grimsby, it's essentially a bowl, so it's deep. So you know the gradients almost don't make sense. But yeah, I think this would be an interesting future project for some kind of AI to try and figure out where those, and then we don't have to put in a freedom of information to the city.
It's like what is the like the minimum available information you need to replicate the swim model with plus AI.
So let me see if I mean the report that city put out before they built the Buka has all the layouts of how the pipes should be laid out, and it's a mess, right? It's a labyrinth of what you think is going here is actually going the other direction because it's essentially zero. Everything is flat, so you really try to like get water to go where it just wants to pour. Interesting.
The Staten Island model where we studied is that it's quite different than New York and Manhattan. New York and Manhattan is quite quick. That happened is a little bit different. So yeah, that your street is I think the swim law does allow you street as a contour so that the water can running off for the running off waters. But the complexity is really huge. To think about that there's a tons of solvents of catch basin and the source, the miles of the source. If you got computer all those units, it's pretty good, yeah. It's time consuming, yeah. So it's very equal. And the big question is, what are the dominant factor? Dominant factor is the rainfall involved in this, and also the infiltration rate and the slope of catch basin. Those are probably some of the most important factors.
Yes. A question about the sensors. Where exactly are the ultrasonic sensors sourced from? Do you make those yourselves or do you buy those?
No, we get those from a company called Matsbotics. It's like the industry standard company that you go to for these kind of sensors. They're just like industrially built. You can have them like chemically resistant as well for an extra cost. In terms of cost, they're probably like half of the cost of the sensor is the ultrasonic. Because you can't cheap out on your one sense that you have. So yeah, they're like $120 for the sensor itself. And then the rest adds up to about $250. And it's developed a long way from here. Like we originally were LoRa based back in the day, then the city requested that we switch to cell. So now we're cellular, so we don't need gateways or other, we don't need, each sensor is an independent device, so it can be deployed anywhere without any reliance on infrastructure apart from a cell signal.
I see. And I noticed the apparatus that you use to hook it over to the pole on the GitHub, are those sometimes 3D printed or upon the similars?
Oh no, always. This is all off-the-shelf type hardware. This one we use less actually, but we use like strut channels, like aluminum strut channels. So it's all very standard kind of McMaster metalwork things. I think that the metalwork is in total is about $20, including all the bolts and things.
I see.
It just like makes it more amenable for other people to use it, right? To build their own versions of it, and it's cheap, easily sourced, and kind of extensible. You can kind of jigsaw them together and like change the way that you do it. because you get like deploying these things is an art form at times. You go out there and the post is bent or twisted or it points just the wrong direction. So you're not over what you need to be over. So you have to go with a toolbox of different attachments to kind of fix at various angles. And then there's a sign that blocks your sun. So you have to then work with the sign. It's a lot of fun, but it's a process to get these things up.
Right, I see. Yeah, there's the image on the GitHub where, the lantern that's kind of backed over like this. So, yeah.
Yeah, the render.
Yeah.
Right. Yes. So all the designs for this version are open sourced. We have newer versions that we do plan to open source in the future, but as soon as you open source something, it kind of takes on a life of its own. So you should generally wait and open source when it's sort of stable position, right? If that makes sense. It's not withholding. It's just like you need to. If people start picking up on it and it's full of bugs, they're going to come back to you and you're going to have to iterate. So it's best to hold off if you can. Yes.
Curious about, you said you had a 15-minute lead time on OEMs alerting, at least for the Ophelia event.
At least for that one location as well. Yeah, there's caveats there. That was
Good line. But I was always, if you wonder, what's the false positive rate on? How often would you
good question. So
trigger what didn't qualify it?
we've tuned the system to optimize reductions of false negatives. I think a false negative is more important to avoid than false positives. The process with our alerting system is you receive an email when the sensor triggers. Any sensor triggers, you get hit with an email, you click a link, and it brings you to a real-time dashboard that's built around Grafana, one of our back-end tools. And then you as a human are looking at that and you're kind of assessing the trajectory up. Because what you're going to see at minute 2 or 3, which is when you get the alert, is the start of something. So the FDNY are a good use case. So when we speak to them about their use of it, they sit there and they have to wait because they're not going to roll out there. They have 2 of these high axle trucks and they're watching an event happening and they're like, right, where do I put those 2 trucks? If they fly them out to where we're saying is a 2-inch flood that then trends down, they've wasted their resource, right? They have to drive it somewhere else. So they will always kind of wait. So there's always a human in the loop tracking the progression. So, it's not automated fully, but it shouldn't be. They
should rather be over notified, monitor them, filter it out.
Yeah, you miss an event fully, that's worse than having to deal with false positives. And there are false positives, it's not perfect. But yeah, there's always a human filter at that stage. Yeah.
I guess it seems like there's different clusters of the sensors around different parts in the cities. Are there densities of it where you're able to see like a more accurate view of the like geographic flooding, or I guess as a second question, like is it possible by comparing it to elevation data by having certain sampling points, you're able to show it in a more geographic context?
It's a good question. So yeah, in the case we do have some denser clusters where you can see there's like time delay between, that this location will trigger first, then a block away you'll get another one. We have limited deployment, so we have that level of density. Staten Island was one use case. Where you saw there was like a clear kind of like cadence between inundation happening. But the fun part is when you bring in the DEM data and start looking at estimating inundation. So we have point measurements, just a point measurement, but we have DEM data, which is 1-foot resolution. So we've been experimenting with just extrapolating out and just like, you could imagine that the sensor gives you one number.
It's flooded in this area is lower level.
Yeah, you're going to have an estimation of inundation over time during an event. And you can also extrapolate and slide that around and kind of see how the pooling would extend. It gets complex when you have to factor in the complexity of the ground. Because we kind of like, we can only assume there's inundation if the pool that we're looking at is beneath our sensor, right? Anything beyond that is a different system as far as we know. So as soon as that pool joins another one, sure, yeah, the inundation is extended, but we've got to be careful. But ultimately, it brings a much richer experience of the event. We're building into our dashboards that visualization so that you can see a 1D or 2D plot and a kind of 3D inundation visualization, which becomes really useful because then you can you can then look at, right, is it covering both lanes of a roadway? We're deploying on some interstates this year. Is it going to cover both lanes? Is the whole interstate going to be off limits? Is the bus route going to be cut? Is the subway entrance going to be inundated? Is it going to be pouring in? It gets really useful, I think. I think with time's up.